Hey everyone, I'm Anish and welcome to PrepFusion. So today we'll be starting the lecture 6 of our root locus chapter of the control system subject, right? So up until now we have basically done basic angle and magnitude condition of root locus. Then we solved the root locus, right? We solved for many characteristics equation, solved the root locus for them. That was for case 1 and part A. What was the part A? Part A was basically for my negative feedback, when my feedback was negative. Now what we'll do, we'll solve 3 other cases. Okay, obviously not solve all of them, just I will give you how to approach the problems there. We'll understand, and also I will take a few examples also. So here, right, this is the basically known as the complementary root locus, right? Okay, if I have my k positive and I have a positive feedback, my k will always be positive and I have a positive feedback, then this will be called as complementary root locus, right? Okay, so here, right, this is normal root locus. If my k is also positive and I have negative feedback, then it is normal root locus. Now if my k is positive and I have also positive feedback, then this will be called as complementary root locus. All this we'll understand, right? Just I am giving you a brief overview of what we will see in the next few slides. So this complementary root locus, right, this is also called as inverse root locus. Okay, inverse root locus. So this is also called as inverse root locus basically, right? So like you can name this anything. So like here, this normal root locus because I have negative feedback. Okay, because overall I have negative feedback, and this will be complementary because overall I have positive feedback. That we'll understand. Okay, so here now one thing I also changed is that my value of k, right, instead of it being a positive parameter, I can make it negative. Okay, so that was basically that you can resemble this one with gain. Okay, and this you can resemble with anything else, right? Okay, I'm not when we will study the controller chapter, there you will understand, right? So here I'm assuming my k can go from 0 to any negative value. It can't go to positive value. So what will happen? So basically, right, so here this, when I have a negative feedback, this will make it look like a positive feedback. How we'll understand? We'll understand, and hence it will become complementary root locus. And even if I have a positive feedback, this will make it look like a negative feedback, right? This will make it look like a negative feedback. Okay, so this is the basic one, so which we know. Let me negative feedback, right? Negative feedback. And what is this one? This one we know, understand, this is like a positive feedback. Okay, but from the signs also you can understand this is positive feedback. Okay, so this is a positive feedback, but the here, right, in the next case the roles will be reversed. Okay, so in the next case, what is happening? Next case, right, if this is negative feedback, then due to this k being negative, this will change it to positive feedback. So this will make it feel like a positive feedback, but this is actually, like, in reality this is a negative feedback system, but due to this k, right, this becomes a positive feedback. If you're not understanding, everything will be cleared, not in this lecture, in the next lecture also. So you have to watch both of this lecture, right? So yeah, I'm just giving you a brief overview right now. I'm not proving anything right now. Okay, so I will prove all this. So this will make it look like, due to k being negative, this will make it positive feedback. And here, as k here also is negative, this will make it like a negative feedback, right? Even though you are seeing here positive feedback, but this will make it look like a negative feedback, but in reality this is positive feedback. Okay, so yeah, just for your notes I'm writing. Obviously we'll prove this one later, right? So just to give you a brief overview of what we'll do, we'll analyze these type of systems, right, where my k is negative, and these type of system where my k is positive but I have a positive feedback. We'll understand that. Okay, so let's analyze the first case Okay, obviously case 1 part A we have done, which is for negative feedback. Now part B is what? It is for positive feedback, right? So when my K is greater than 0 and it is positive feedback, there is a part B. So here, right, simple block diagram I have written, okay, and my K is positive, right, between infinity and 0, okay, positive infinity and 0. Now what will my closed loop transfer function become when I have a positive feedback? I hope you remember, right? So I hope that hasn't gone away from your memory or something. Like, what was the formula for my CLTF? CLTF, that is y of s upon, no, not y, what is c of s upon r of s. C of s upon r of s. What was the formula? It was g upon 1 minus gh, right? G of s no, it was minus, right? Here it was minus, not plus. So what does my closed loop characteristics equation become? So my closed loop characteristics equation, it becomes 1 minus g of s into h of s, right, which is equals to 0 itself. 1 minus g of s into h of s, which is equals to 0 itself. So here, right, it has changed from plus to minus. Okay, so what does change due to this? What, remember what condition just changed? So when we study the normal root locus, right, initial phase, so what did we first derive about what is this? This is the OLTF, right? What did we derive? We derived two things, right? I hope you remember. One was the magnitude condition, another was the angle condition. So can you tell me what changes here? Just think your brain, and what condition change here? Okay, so what condition changes? Like, I can write my g of h of s, like here only, my g of h of s. What does this become? This becomes 1, right? So this is lying on the positive x-axis, right? Positive x-axis. Okay, so if my g of h of s equals to 1, then what does this mean? Let me delete this, paste this and color this. So this means basically I have two conditions. One is the magnitude condition, another one is, okay, I should draw this in straight plane because not looking good. Okay, one is the magnitude condition and another one is the angle condition. So what does the magnitude is? The magnitude, right, like this has to satisfy this any test point that I take, right? Let's say I have taken a test point s equals to st. So for it to lie on my root locus, that has to satisfy this condition, right? This condition, that g of st into h of st equals to 1. So my magnitude of that, right, OLTF should be equals to 1. Magnitude of my OLTF should be equals to 1. Now what should my angle be this time, right? My angle should be, you can say 0, or you can say even multiple of pi, or it is a multiple of 360 itself, right? So my angle, that condition changes, instead of odd multiple of pi, it changes to even multiple of pi. Can write it like this one, 360 times k, right? So like why? Because this is my plus 1 is on the real axis, right? That's why. So my plus 1 is on the real axis. K equals to 0, 1, 2, and it is keeping on going, right? So now, right, it will be even multiple of pi instead of being odd multiple of pi. So I will write angle of OLTF should be even multiple of pi. Okay, so angle of OLTF should be even multiple of pi. Okay, so this is this one. So what is my standard OLTF? So like we already know, right? That won't change. What is my standard OLTF? So my standard OLTF, right, it was g of s into h of s, which is equals to k into s plus z1, and it is keeping on going like this, s plus zm, s plus p1, s plus pn, right, which is k greater than 0. Okay, so k greater than 0. So like for here, like k is greater than that, we know. Okay, so this is my standard OLT basically. Now what whatever steps that we used previously, right, for like this rules that we use, right, to plot my root locus will now change. Exactly where will it change? Wherever that angle condition was used, right? So I have intuitively used angle condition to prove few rules, right? So wherever I use that angle condition, okay, so that will change now. So now you can understand why I have given you the intuition, right? So here you can understand why does this rule change and why this rule doesn't change. So wherever I've used that angle condition to prove that rule, right, so there that rule will change, because here the angle isn't a odd multiple of pi anymore, it is a even multiple of pi, right? So yeah, so previously wherever we used the angle condition for sketching the root locus, that will now change. Like those rules will now change, sorry, those rules will now change. Those rules will now change. Okay, so yeah, this was the like the short note. Now let's come to the rules basically. So what are my rules for sketching the complementary root locus? So this is my characteristic equation. What is changed? This sign is changed, right? This sign is changed. Okay, just be careful about this one. This sign is changed. So I'm going to highlight this. This sign is changed. Okay, so with positive feedback, my characteristic equation with positive feedback becomes 1 minus, right? So the like this already we know that it will have n branches, right, because it has n roots, and like other will be asymptotes, basically virtual zeros. So but what will be different here? This, right, we have to locate the open loop zeros and poles, and like they will start from poles and they will terminate at zeros. This will still remain same. This won't change. Okay, this won't change. What will change is, instead, like here, no, here anything won't change, so this will still be same. This will still be same. Okay, this will still be same. Oh no, I can't write E. I'm so sorry. Okay, this will be same. Now will this rule to change? So what method did you use to prove this rule, right? We use the angle condition, right? What condition did you use? We use the angle condition for proving this rule. I hope you remember we proved that like due to complex pole, this angle won't matter because both of them will cancel out, right, at the real axis, and only the poles in the real axis will matter. And if it was a odd multiple, right, if it was angle was an odd multiple of pi, then this point will lie on the root locus, and from there we derive that the number of root poles and zeros taken together should be odd for that test point on the right hand side of the test point for that test point to lie on the real axis of the root locus. So here, right, it changed to even. I hope you understand why even, right? So here the angle condition has become 0. As the angle condition has become 0, then, like, let's say I will just draw here. Let's say I have a pole over here, and I want to check for this test point, right? This test point. Now, what is the angle from this from this pole to this test point? It is -180. So does it satisfy my angle condition for positive feedback? No, it doesn't. Right? So hence this is not possible. Hence odd number of poles and zeros on the right hand side of my test point is not possible. So what other thing is possible? What is possible is even number, right? Or 0, even or 0. So if I take my test point here, what I see, what is my angle from this pole, right? It is lying on this axis only. I hope you remember, right? We measure the angle with respect to x-axis. So it is 0 degrees. So if it is 0 degrees, this does satisfy my angle condition. Okay, does satisfy my angle condition. So hence this will lie on the root locus. So from here I can deduce that the number of poles and zeros should be even. Okay, so this, right, this has changed. Okay, so let me reduce this one actually. Now what else has changed? So does the asymptote condition has changed? Yes, right. Try to remember when we proved the condition for asymptote, right? We used it with the angle condition. Okay, with the help of angle condition. So there what we derived was, so that theta asymptote should be equals to 180, something like that, right? So I hope you remember, right? So everything cancels out and then we get 180 and this p minus or something. Okay, so just go back to the proof, there you will remember. Just instead of 180 you write 360 there, or 0. Okay, not 0, you write 360 there. Okay, then what do you get? Like 360 and 0 same only. Okay, I have your no. So if you write 360 over there, you will get this formula, basically the same. Just instead of 180 I'm writing 360 because my angle condition has changed this time. Okay, my angle condition has changed. Okay, so this is my angle condition, so this has changed. Now what about my centroid at point of intersection of asymptotes? Now I haven't proved this one, but my centroid, right, we proved this centroid with without the angle condition. So this will not change, so this will remain same. Remain same, right? This will remain same. Now what about like the breakaway and breaking point? So the thing to keep in mind is that my characteristics equation has changed, but this polynomial, like for the positive and negative feedback, a of s upon b of s hasn't changed. Okay, a of s upon b of s hasn't changed. Just what will change is that, like, y like a of s is changed to minus a of s, if you want to say it like that this was plus, right? So a of s has changed to minus a of s, but why it won't make a difference? Because what we used to do was, basically we used to do a of s into b of s minus a dash of s into, sorry, this is b dash of s equals to 0. Now you might ask, like, if I change my a of s, let's say to minus a of okay, let me name this one. Let's name this one like a1 of s equals to minus a of s. Okay, so this will be 1 plus k a1 of s upon b of s. So I hope this equation is similar, right? This equation is similar to negative feedback. So here it is a1 of s and b of s. So let me write this one as a1 of s and a1 dash of s. So just replace a1 of s with minus a of s. What you will see is it doesn't matter. Minus will get cancelled, and again I will get the same equation. Okay, I will get the same equation. Okay, so what is the main point I'm getting at is my solutions. So I will write here in the next page, it is already written that the solutions, right, the solution of the equation will be same as the normal root locus or case A. So solutions of this equation will remain same, will remain same. Okay, solution of this equation will remain same. So like one thing I forgot to mention at the starting of the lecture is that don't worry, okay, this complementary root locus, right, 99% of the cases, like on I can say 90% of the cases, okay, this one comes. So even if you don't understand, like I know, like I'm teaching you so well, you will understand this, but by chance it feels hard to you or something, 90% of the cases, okay, which color should I choose? I'm still debated which color. So this one is the 90% case, right, 90% case, okay, and this one, let's say this one is the 5% case, or let's say 6% case, something like that. And all these, right, all these are very rare chances, this come very rare, okay, like these two cases, right, very rare. This is the main 90%, main target should be this one. After finishing this one well enough, then you follow this complementary locus, right? So yeah, that I wanted to mention, I just forgot to mention at the start of the lecture. So yeah, so now let's come back to where we were here, right? We were here. So here the solutions will remain same, but what will change? The valid points, right, valid test points will change now. Okay, whatever the valid test points were there, here this won't be. Why? Because the value of k won't come positive for the previous valid points. Okay, you just check, you will understand. So just keep this in mind, that the characteristic equation has changed, so the value of k will also change. Okay, so what will be the value of k? So initially what was my value of k? Value of k won't be any more minus b of s upon a of s. It won't be any more minus b of s upon a of s at that particular test point. Okay, s equals to st at that particular test point. It won't be, right? What will it be? It will be k equals to sst equals to b of s upon a of s. This time it will be positive, right? That's why like my k has to be positive, right? K has to be positive. So I've taken the k's part b, right, of this one. So k is positive here, k is not negative. K is negative, hasn't even come yet, so k will be always positive. So for k to be positive, if I put the same values, right, of the previous, like the normal root locus, okay, in the negative feedback, then my k won't come positive anymore, k will come negative. So yeah, this, like once we do an example there, you will see, and I will tell you the difference also between the normal root locus and the complementary root locus. So like that was that rule. Okay, for the breakaway and breaking point, like the breakaway breaking point rules are same, that they have to lie between two poles for the breakaway point, and for breaking point they have to lie between two zeros. All those things are same. Okay, but just the valid location have changed, right? Valid location has changed. Once we do the example, you will understand. So now, and what about the angle of departure? Just remember, did we use the angle condition? We use the angle condition for the proving the angle of departure and the angle of arrival, right? So here, right, it will also change, will change. What will it change to? It will change to 0 degree, right? It will change to 0 degree, right? Here there was 180 degrees, so instead of writing 180, now I can write 0 or 360, whatever you choose, right? You can write 0 or 360, whatever you choose, right? So yeah, this will change to 0. Now this angle of arrival will also change, like both of them use the same types of proof only. Okay, so this will also change to 0 degrees. No need of further explanation. Okay, you just put there in the proof, instead of 180 you prove 0, and you will get this answer, right? So now what about the points, crossover points, right? What about the crossover points? So in crossover points, what we used to do? What do we used to do? We used to put s equals to j omega. Now if we used to put s equals to j omega, does this use angle condition? No, right? It doesn't use angle condition. Doesn't use angle condition. So if it doesn't use angle condition, so this will still remain same. Okay, this rule will still remain same. So I will like at the end of this chapter, right, root locus chapter, I will briefly summarize what will say remain same, what will not same remain same, that is right. So that will I will do, try to summarize in the end of the last lecture, or like in separate lecture itself. So yeah, then you obviously sketch your complementary root locus. So now let's do a example, and from there we will get a better understanding of how to solve complementary root locus, right? So here I have to plot the root locus diagram for the following OLTF. So they haven't told us about anything about complementary, just have to told us to plot the root locus. So what is root locus? Root locus is the trace of the closed loop poles, right? So root locus is the trace of the closed loop poles. Complementary, we have named it for our better understanding. That just be careful, here the rules have changed. Here the rules have changed. Root locus definition is same only, right? So it is basically the trace or path of the closed loop poles with the help of open loop poles, right? By varying my parameter, system parameter k. Okay, so yeah, that what we will do here. That is what we will do here, right? So now, like, try to do it by yourself first, then I will do it, right? So first, what was the rule? We have to locate the open loop poles and zeros. That remains same, right? So n was the number of open loop zeros, n was the number of open loop poles, and m was the number of open loop zeros. This we can write as, few people write it as p and z. Whatever you whatever you are suitable with, you choose that. So yeah, that one is that one. Now, how many open loop zeros and open loop poles do we have here? So we have, right, we have one open loop zero and two open loop poles. So p is 2 and z is 1. Okay, so I will have one asymptote, right? I will have one asymptote, that I know, that won't change. Okay, so because at k tending to infinity, obviously it has to terminate to two zeros, right? Two zeros, so one will be virtual 0. So I will have two branches, hence branches will be 2. Okay, branches will be 2. Now what else my, so let me plot the zeros, right? 0 is here only. Okay, 0 is here, -8, and pole is at -4, and this is at minus 2, right? So this is at -2. So all these values, right? So this, for this value k will be 0, for this value k will be 0, and for this value k will be infinity. Okay, so this will terminate at infinity. That won't change, right? That will still remain same. So root locus will have two branches, as the order of characteristic equation is 2. That we cleared. So now what is my characteristics equation? So what is my characteristic equation? This is a positive feedback, right? Positive feedback. So what does my characteristics equation become? It becomes 1 minus g of s equal to 0, right? So 1 minus g of s equal to 0, which is simply 1 minus this one, right? K into s plus 8 divided by s plus 2 into s plus 4. Okay, so this one will become this one, which is equals to 0, right? So now what was the next step that we used to do? We should do the where does my root locus lie on the real axis, right? Where does my test point lie on the real axis? That we do, okay, by just checking the even number of poles and zeros. Okay, so just let me take this one. Okay, this is already here, so okay, I will just take the previous one because easier for me to, again I have to draw the poles and stuff. So here, right, if I see, what do I see? Like, I have to find the even number of poles and zeros, right, this time, and or zero number of poles and zeros. So here in this location I have no poles and zero on the right hand side of my test point. If I pick a test point here, so on the right hand side of my test point I don't have any poles and zeros. So what can I say? That my root locus will lie in this range, right? This will lie in this range, and my root locus here, right? Again, if I pick a test point here on the right hand side of my test point, what do I see? I have two poles. Okay, so even number of poles. So my root locus will lie in this range also. Okay, but will my root locus lie in this range? Will it? If I take any point and see the right hand side of my test point, what do I see? I see three pole zeros, right? So it is odd, right? Hence it will not lie in the root locus. So this is correct, this is correct. So my test point, right, my test point will belong to -8, -4, union -2 and positive infinity, right? So my test point will belong in this region. Okay, I hope you got it. So here what will happen, here I will have a virtual zero basically, that we will do in the next step, right? So we have to determine the asymptote and the angle of asymptotes. So everything is same, just the formula has changed. So if I put p minus z equals to 1, because p minus z equals 2, so what does my angle of asymptote becomes? So like k starts from 0, right? K starts from 0. So theta asymptote p minus z is 1 itself. So theta asymptote is 0 degree. Theta asymptote is 0 degree itself, right? So my theta asymptote is 0 degree. So like basically here, right, it is on the positive x-axis, so it is not at any angle. So this will be like this one, like asymptote will be present. And what about the centroid? No, like the asymptote is on the real axis itself. Only the asymptote, only one asymptote we have, and it is on the real axis itself. So obviously there will be no concept of centroid, okay, as my asymptote is on the real axis. Okay, so I have got it. Now we'll determine the breakaway and breaking point. Here this one will be interesting. Okay, so if you go back, right, like whatever example I have taken, this is the first example that we used, right, for plotting the root locus. So there if you check, the solutions will be same, right? The solutions will be same, but what will be different, let's see. So like again I will take the characteristics equation. Okay, where was my, yeah, this one, right? I will take this one. If I take this one, right, if I take this one, what will happen? My a of s, my a of s is basically s plus 8, and b of s is s plus 2 and s plus 4. Okay, so this is my a of s and b of s. So if you see, right, if you solve this, okay, I have written it down here also. Okay, I have written it down here also, that what will happen is that basically only those values of s will be valid by solving equation 1. This is the equation 1 basically. This is the equation 1, sorry. Okay, I've already written here also equation 1, for which in which my system parameter k is positive. Okay, so yeah, those points will be valid. Okay, we'll see, like my system parameter k, right, is this time this, right? My system parameter k is this. So only those values of s will be valid, as I mentioned earlier also, that if I put that value of s and my k becomes positive, then it is valid test point or valid break-in or breakaway point. Else if it comes negative, if my value of k comes negative, it will be invalid point, right? So that you have to understand. So yeah, now let's solve this. Like if you solve this, right, you will get the same solutions as the previous one, same 3 points you will get, right? So okay, again I have to solve this. So what does the, okay, what was the equation basically? Okay, I deleted that one, but I shouldn't have deleted. Okay, what was the equation? Just hold on a second. So this a dash of s is 1 itself. What is this b dash of s? B dash of s is s plus 2 plus s plus 4, right? So b dash of s is s plus 2 plus s plus 4, which is 2s plus 6. Okay, which is 2s plus 6. So this is my b dash of s is. So now, right, let's simply use that equation. Okay, use that equation. Okay, sorry, okay, I didn't write the equation 1, sorry. The equation 1 was actually this one, sorry. My equation 1 was this one, right? A of s b dash of s minus, sorry for my mistake. So I was talking about this equation, a dash of s into b of s. So this is the condition for my break away or in point, right? This equation has to be satisfied. So that, sorry, I was saying about that one, that break in or break away point has to satisfy this equation. Okay, so that I will get the roots of this equation will be my breakaway or breaking point, potential breakaway or breaking points. Now out of those points, if my k value is not positive, obviously it won't be a valid breakaway point, right, or breaking point. Okay, so like this also we have established in the normal root locus also, right? So now let's do this. So solving this equation, right, so what can I see? So this like a of s into b dash of s, so a of s is s plus 8 into b dash of s is 2s plus 6. A of s is s plus 8 into b dash of s is 2s plus 6. That is that one. Okay, and then we're minus a dash of s, minus a dash of s. A dash of s is 1, and my b of s is it is basically, I can write s square plus 6x plus 8, right? So six s plus 8, right? So this is my b dash of ss, so this is equals to 0 itself, this is equals to 0 itself. So this is equal to 0 itself. So like if you solve this right, I won't solve this, I've already written down the solutions, won't waste time. So my s potential breaking points, right, is break points potentially comes out to be, like, we have 2 points, which is minus 12.85 and what was the other one? It was minus 3.15, right? Okay, so will they lie on the root locus? Are they valid breakpoints? Okay, valid breakpoints. Are they valid breakpoints? So for that, let's check what range of my test point s is lying on the real axis, right? That we have already established. From there also we can simply understand that whether like we will have a breakpoint or not. Okay, like from here itself, right, from here itself we can understand, right? Not here. Okay, I haven't done that yet. Okay, that's fine. So my test point, right, will lie along this line. So from here itself we can understand where will my will there be a breakaway point or not. So basically, right, I'm like starting my root locus from here and it is directly ending to this 0, right? Directly ending to this 0. This is gone, and similarly I will start my root locus here and this will directly end to the virtual 0. Basically, I know the angle of asymptotes, right? They're 0, right? 0. I have only one asymptote and that is 0. So can I see any breakaway or breaking point? No, right? So that is already, we know from intuition itself that we won't have any breakaway or breaking point. But like to prove you that here, right, if I put this the valid points on the real axis, what do we say? This is also not lying on the range, right? Not lying on the range, and this is also not lying on the range, right? Okay, so both of them, right? No, both of them will not lie on my root locus, hence I don't have a valid breakpoint. But like if you go back to your notes, you will see that the two roots, right, are same, but they were valid breakpoints there. Here they weren't. Why? Because if you check for k, right, check for k, right, I've already like written the calculations down, so you do it by yourself. So check for k, what will be k equals to? K will be equals to, like, ks equals to, let's write this as minus 3.15, and basically this will be b of s upon a of s. Okay, b of s upon a of s, that is like not minus this time, not minus. That's why that was making a difference, right? There was a minus sign outside that was making my k positive. Now I don't have a minus sign outside, okay, of this b of s, so that will make my k as negative. So my k will come out to be minus 2.5, which is not valid. Okay, and for the second case, right, for the second case, what do I see? I see that I have minus 12.85. like there it was coming positive 0.2, here it is coming minus 0.2, that's why it is not valid. And like if I put k equals to minus 12.85, so previously it was coming, I think it was coming, yeah, plus 20. Okay, now it will come minus 20 again, right? Both of them will not lie on the root locus, right? So will not lie on the root locus. So like one thing I hope you understood, that complementary root locus and root locus are not anything different, right? So here also we are plotting the trace of the path of the closed loop poles itself, right, of the system, right? Just what is changed is the from negative feedback it has changed to positive feedback. So obviously few rules will change, right, conditions will change, but it is just root locus only. So don't get scared that complementary root locus is something god given different thing, because during my preparation also I was scared, right, of this complementary root locus. Okay, but then after like studying it a bit, then I understood that it is nothing different, right? Just here I have positive feedback instead of negative feedback. That's why few rules changed. Okay, and those rules changed. Why? Because the angle condition changed, right? Okay, so yeah, so hence we'll have no breakaway or breaking points. So no breakaway breaking points we'll have. So now what we'll do the calculation of angle of arrival and departure, but obviously as we don't have any complex pole, so we'll skip that one. So we'll skip that part. So now we'll directly move to the step 6. Okay, so I will write step 5 skip. As no complex pole present. No complex pole present. So now what we'll do, we'll go for the crossover point basically. So this is step 6, which is the crossover point. So we have to determine the points where my root locus may cross the imaginary axis. So here the procedure is same, we just put s equals to j omega. Okay, so if you put s equals to j omega, just what will change is that the crossover points will also change. Why? Because my characteristics equation has changed, but the rule will still remain same, nothing different will happen. But here it will become just a bit tricky. Why? We'll see. So what we'll do, we'll put s equals to j omega in characteristics equation. In characteristics equation we'll put s equals to j omega. Okay, so let me copy the characteristics equation. So this was here, right? Yeah. So if I put this one, right, if I put this one, so like what like let me write the characteristic equation. It is s square plus 6s plus 8 minus k s plus 8 equals to 0. Okay, so now what we can write, s square plus s into 6 minus k plus 8 minus 8k equals to 0, right? So this is my characteristic equation. Now we'll put s equals to j omega here. So what will I get by putting that? So if I put s equals to j omega, this becomes j omega whole square plus j omega or this differently. So what will this equation become? So this will be minus omega square, this will remain j omega minus 6k, and this will be plus 8 minus 8k basically. Okay, so this is this one. Now, right, we will equate the real and imaginary parts. That is basically, first what we will do, we will equate the imaginary part of my characteristic equation, imaginary part of my 1 plus gs, right, or 1 minus gs, like it is positive feedback, is equals to 0. So if I do that, what I will get that my omega into 6 minus k equals to 0. So I can have two solutions. Like previously I ignored one solution, omega equals to 0, I know, right, previously. Why? Because if you put omega equals to 0 there, you would have gotten k as negative. But here what will happen? Quite the opposite will happen. So I will have two solutions. Which one will you choose? One is omega equals to 0. Another one is k equals to 6, right? 6 minus k is 0, so k equals 6. That one you can choose, right? So if we choose these two, which one should you get? So if we choose omega equals to 0, right? If we choose omega equals to 0, then what you do, you make the real component 0, right? Real component equated to 0. You make omega 0, this one goes to 0. And what does this become? This makes my k equals to 1. Okay, 8 minus 8k equals 0. So my k is 1. Okay, my k is 1. Now if my k is equals to 6, what happens? My k is equal to 6. So here, right, what happens is that, like, this becomes minus 40 and omega squared is equals to minus 40. Omega comes out to something imaginary, which is not possible. Omega is real value. S is imaginary, but omega is real. So omega here, it comes out to be plus minus j40, so which is not possible. My frequency should be real, right? But like the value of s is imaginary, that is okay. S equals to j omega, that's why s is imaginary, but omega is real. So omega should be real, right? Hence we ignore this solution and we accept the solution. Like from intuition you can directly say that it will lie on my s equals to 0. Okay, how? From here only you can understand, right? Where was I? Okay, it was like from here only you can understand. This one will go on, right, and it crosses at s equals to 0. So like from here we can understand omega is 0, that is fine. Okay, but there I just gave you the reasoning behind why omega 0 is valid and other points are invalid, right? So yeah, that is that one. So if you put omega 0, you get k equals to 1. So that is fine. So you can also, like, what is the homework for you? Homework for you is validate using Routh-Hurwitz, right? So this is the homework for you. Validate using the Routh-Hurwitz criterion. Right. So now like this is the homework for you. I will write this down in the notes and there you can cross verify, right? I won't waste time. So you draw the RH table, you use the characteristic equation, and there you will understand, right? So just let me make the straight lines better. Okay, so yeah, I won't mention anything. So what I will do is that I will just copy. Okay, maybe I have drawn it already, is it? Okay, I haven't drawn it, so I will just okay, what I will do is I will delete this one. Actually, I'll just copy the previous one, right? So if that previous one is copied or not, no, that is not that one. I will just copy that previous one and completely draw up my root locus here, and I will show you the difference between the actual root locus and the complementary root locus, right? Like not the actual, when I have a positive feedback and when I have a negative feedback, what is the difference? Let's check that one out. What was I here, right? Okay, here. Okay, maybe okay, this is here only. Okay, fine. This I will make bigger. Okay, and I will also copy the characteristics equation. Where is the character? Yeah, here, right? What I can write, g of s equals to So g of s is this one. So now right now, so basically this one will go until this asymptote, this one will go until this asymptote. I won't have any breakpoints here, right? I won't have a breakpoints here, so that is fine. Right now, this is the crossover point. I hope we got that. So at crossover point, what is the value of k? K is 1 over here, right? K is 1. Okay, so I won't have any breakaway point. So this is my simple root locus. Very simple, right? Complementary root locus is very simple. Don't scare away from this one. So now if you observe, like, this was my normal root locus. This was so difficult, right? So like what happened actually? So here, right, between -8 to -4 I don't have anything, but here I have, right? I have. Okay, so complementary, that's where the complementary name comes from, right? So whatever I don't have here, like in the real axis, that's just the opposite. So like this you can remember, right? So whatever I don't like, whichever points don't lie in my real axis of my root locus, in the normal root locus with a negative feedback, will lie here, right? It will just be the complement of that one. Complement, the real axis will be the complement of that one. Imaginary, I can say, why is it complement? Because here, right, the condition changed, right? I need to have even number of poles of zeros instead of odd number of poles of zeros. That's why it became complementary. Okay, that's why it became complementary. So yeah, this is this one. Okay, so yeah, I hope we got the difference between the root locus of with negative feedback and positive feedback. So is there anything else you observe in this, like in this root locus and in this root locus? Do you observe something that here, right, I don't have any crossover points? Basically my poles, closed loop poles, are never leaving my left half plane, right, for any value of k, but here they are leaving for few values of k. So what does this mean? Like as I mentioned earlier also, right, like in the first few chapters, that what the feedback part, right, that my positive feedback reduces the stability. So here from the root locus diagram, I can see that my positive feedback reduces stability, right? So that's why we generally tend to avoid use of the positive feedback. Okay, so yeah, that is basically it for this lecture. The homework part you do, right, prove that condition of crossover point for using the RH table. So in the next lecture we will also do few solutions, like examples and bit of concepts I will give you about the other two cases, right? Now if my k is negative, what will happen, that we will understand, right? So I hope you revise this one. If this one gone over your head, I try to explain it as much simpler as possible. Okay, explaining everything, why did rule change, why did this rule change, and why did this rule didn't change. So I try to explain everything, right? So let's get a brief overview, like exactly what things you have to keep in mind. Exactly what you have to keep in mind is that my k is positive, and I'm using a positive feedback. So if I'm using a positive feedback, what will change? My characteristic equation will change because the denominator has changed, right? So denominator has changed. So if my denominator, okay, oh no, I have to again go back. So if my denominator has changed, right, like if my denominator has changed, okay, then my characteristic equation has changed, then my OLTF condition for any test point to lie in that in the CLTF, right, basically the poles should be equal to 0. For me to follow the characteristic equation, the condition has changed. It has become +1 instead of -1. So magnitude will be same, equals to 1 only, but my angle condition will change. It will be ±360, right? ±360. Okay, so it is basically even multiple of pi. So wherever for sketching the root locus, the rules that I have used, where the angle condition has been used, right? Okay, wherever I use the angle condition to prove the rules, there the rules will change. Instead of 180, I will write 360. Okay, so yeah, this has changed. So here this will remain same, right? The it will start from open loop zeros and open loop poles, so that will remain same. Even if you make k tends to 0 or k tends to infinity, that minus sign, right, doesn't make any difference. Okay, minus sign doesn't make any difference, but here it will make a difference. Okay, why? Because we have used the angle condition. That's why that real axis part, okay, my on the right hand side of my test point, even number of poles and zeros or zeros should lie right on the right hand side of my test point. Okay, then it will be a valid root locus, right, valid point on the root locus. Okay, so yeah, my angle of asymptote will change because I have used my angle condition to prove this one. Centroid, no, it won't change. I haven't used, like I haven't proved it, so it is not that important also. So here it won't change, right? So breakaway breaking points will remain same, but the values of k will change, and the valid breakaway and breaking points will change. Okay, because they will be the just the inverse of that one. Okay, so what I can write is they will be the complementary of my previous one, because as I mentioned, right, whatever was present in my on the real axis, whatever was present in my normal root locus, it will be complementary in the real axis, right? So what I can say, complementary of previous one. Complementary of normal root locus. What do I mean by complementary of normal root locus? Basically, whatever solutions I rejected there, that will be taken here, right? So whenever I solve the that equation, right, that a of s into b of a, b dash of s minus a dash of s into b of s equals 0. Whenever I solve that condition, right, whenever I solve that condition, I get many values of s. Few I reject and few I accept, right? So whichever accepted I there, I will reject here, because the equation will be same only, right? Equation will be same only, so solutions I will get same, but whichever I reject there, I will accept here, and whichever I accepted there, I will reject here. Okay, just be complement, opposite of that one. Okay, so yeah, from here you can understand. So whatever in the real axis, right, everything becomes complementary. Everything becomes complement of my actual root locus. So yeah, solution will be same, but which solutions I will take and leave, that will flip, that will change, right? That will change. Okay, so yeah, that we got, and value of k, just be careful, this time it is not minus b upon s, it is minus plus b upon a, right? So angle of departure will also change. I will put, instead of 180, I will put 0. This will also change. So again, right, determine the root locus may cross this, like this, it won't change. And yeah, we solved the example. So yeah, this was the basically the complementary root locus. In the next lecture, we'll do a few more examples, and we'll understand what happens when my value of system parameter k becomes negative. Yeah, thank you for watching.